This is Sam Daulton. I'll be presenting our work on Distilled Thompson Sampling via Imitation Learning. This is joint work with Namkoong and Eytan Bakshy. I'll begin with a motivating example on adaptive bitrate control for video streaming. I'll describe the contextual bandit problem, the Thompson sampling algorithm, and some of the practical challenges of using Thompson sampling in real-world applications. I'll walk through our imitation learning method, describe some of its theoretical properties, and present some of its empirical results. As a motivating example, we consider the video streaming quality optimization problem. Performant video streaming is critical for providing a high-quality user experience in many media applications. The 2017 Video Streaming Perceptions Report found that 92.9% of users had abandoned a video due to issues related to stalling, load time, or poor video quality during playback. Many media companies now use adaptive bitrate controllers to optimize the quality of experience. Given an estimate of the bandwidth and the current buffer capacity, the bitrate controller selects the next bitrate to use and sends that request to the server. In response, it receives a new video chunk, which is passed to the buffer, and a new estimate of the bandwidth is created. As the video is streamed to the user, quality of experience metrics are provided back to the bitrate controller. Frequently, the bitrate controller is embedded within the device to provide low latency decision-making even under poor network conditions. This enables the best quality of experience during video playback. This is often treated as a contextual bandit problem. A contextual bandit problem is a sequential decision-making problem where at each time step, the policy receives a set of contextual features. Given those features, the policy decides an action to take. That action is performed, and conditional upon the context and the action, a reward is received. The context, the action, and the reward form an observation tuple, and the collection of this history is used to update the policy. The goal in a contextual bandit problem is to maximize cumulative rewards. Thompson sampling is a popular algorithm for contextual bandit problems. Thompson sampling selects actions with probability proportional to an action being optimal. Thompson sampling relies on a posterior distribution over the unknown reward function. At each time step, a sample is drawn from that posterior distribution and optimized using numerical methods to find the action that has the maximum expected reward under that posterior draw. These two steps, posterior sampling and numerical optimization, are both computationally intensive. This high computation cost poses practical challenges in low latency applications where high latency degrades the user experience. This problem is exacerbated on slow processing units on older phones. An additional challenge is on-device deployment, where devices often have limited memory and model size becomes a critical concern. Lastly, despite recent advances in software for supporting deploying deep learning models, there is limited support for deploying probabilistic models. To address these practical challenges, we propose to distill a Thompson sampling policy via imitation learning. Given a probabilistic model with an implicit Thompson sampling policy, we propose to learn an explicit policy representation. This explicit policy can be used for fast online decision-making while retaining a principled exploration strategy using Thompson sampling. The imitation learning objective is to train a model to minimize the expected discrepancy between the Thompson sampling policy and the imitation policy. Using KL divergence as the discrepancy measure and a finite sample approximation based on observed contexts, this is equivalent to a maximum likelihood estimation problem. Although the imitation learning objective involves a potentially high-dimensional integral over an unknown marginal distribution, there often are abundant unlabeled contexts available in many practical applications. Here, unlabeled means that there is no corresponding action or reward, only contexts are necessary. For example, many large web services will have databases containing contextual information about different entities. Given a Thompson sampling policy, our imitation algorithm proceeds as follows. First, we draw posterior samples from the posterior distribution. Second, we sample contexts and perform numerical optimization on each of the posterior draws. This gives us an estimate of the Thompson sampling policy for the given context and history. We use this data set of contexts and empirical policies to train an imitation model. Importantly, our imitation learning algorithm shifts the heavy computation involved in posterior sampling and numerical optimization from the online setting to the offline setting. The explicit imitation policy can then be deployed in the online setting for fast online decision making. New observations that are collected under the imitation policy can be passed back to the Thompson sampling policy for offline batch posterior updates. It is important to note that new observations are collected under the imitation policy, not the Thompson sampling policy. To be clear, the actions are generated under the imitation policy, not the Thompson sampling policy. Therefore, our imitation learning algorithm emulates an off-policy variant of Thompson sampling. We characterize the performance of our imitation learning algorithm by first relating our imitation learning algorithm to off-policy Thompson sampling. We then relate off-policy Thompson sampling to UCB algorithms to derive the following regret bound. We find that our imitation learning algorithm enjoys the same Bayes regret as the best UCB algorithm up to a sum of single time-step imitation errors. Importantly, these errors can be easily controlled in the presence of abundant unlabeled contexts. The error scales inversely with the square root of the number of unlabeled contexts that are available for imitation learning. Empirically, we find that there is no difference between the imitation policy and the Thompson sampling policy in terms of cumulative reward. Our empirical evaluation includes a benchmark problem with real data from Instagram video upload optimization. Our wall time measurements show that our imitation learning algorithm reduces decision-making latency by over an order of magnitude. This imitation learning algorithm has been deployed in production at Facebook and Instagram for optimizing video upload quality on posts and stories. In our paper, we provide concrete Bayes regret bounds for two modeling scenarios. In addition, we provide generalization guarantees for finite sample approximations of the imitation learning objective, as well as additional empirical evaluation on real-world datasets. Please check out our paper if you're interested in learning more. I'd like to thank Sean Singh and the Facebook Adaptive Experimentation team for their support. Thank you.